our presentation. Our speaker tonight is Greg Huber. Greg was president of FOTO when I first joined, so it's been around a long time. I have almost forgiven him for being born just after we landed on the moon.
That's correct, yes. It dates me a little bit. Oh, yes.
So, but he's been a long-time member and a terrific speaker. So without further ado,
thank you.
I will move it up.
I just before I get started, it's kind of, I'm sort of emotional to be in this spot. Like 1996, I was part of this first little meeting we had with FOTO. I think it was John, Dave, and Sheila was in this room. There were like 5 of us, and this was going to be the start of look at all the people here today to do this, and it's just really wonderful to have such a great group of people and to watch it grow and to be welcomed back. Like all of you guys, I took some time off to get my children grown up and try to boot them out of the house and that kind of stuff. And, I came back, and as if I had all of my old classmates and friends were like, come on, and talking astronomy again and getting fired up. It is wonderful to be back here at the observatory. Thank you all for having me back. I'm glad I can help out. And I'm not going to be a stranger nearly as much anymore. That's a promise and not a threat is what that is. That's the way that works. Valerie called me up, I don't know, a couple months ago. She's 9 months ahead on photo programs. You can't beat that. And said, hey, would you mind doing something? And I kind of rolled it around and said, throw me into May. And we'll do the small exploration of the Fermi Paradox, which has been rolling around in my head for a while as a presentation to do for you guys. So without further ado, we'll title it, Where is Everybody? An exploration of the Fermi Paradox. And you don't have to know any math. We'll talk a little bit about the science. I saw the title of your program and thought, man, you should have gone first, because I'll just touch on a little bit of that extrasolar planets here. There are some disclaimers that we will start with first. Much of this presentation is based upon Stephen Webb's book, Where If the Universe is Teeming with Aliens, Where is Everybody? Second edition, it came out in 2015. There it is. Each slide of the presentation could probably be its own full-blown photo presentation. So there's your next 3 years of photo presentations for each slide coming up in the presentation. So we're going to go really fast over some of these things. So probably lots of questions. Feel free to chime in or throw your 2 cents worth in as we go here. The history, first proposed by a Russian rocket scientist years ago, was in an unpublished paper. He had written it down and said, there must be other life out there. We don't see it, but there must be other life out in the galaxy. But it got its name from Enrico Fermi back in the 1950s while discussing with some of his colleagues light speed travel. Like, what would it take to travel around the galaxy and zip to and from the stars? And mid-sentence, he exclaims, where the hell is everybody? Like, if there are aliens out there, why have we not heard from them yet? And since then, dozens and dozens of ideas have come up as to solve or explain this seeming paradox. And today's presentation, like I said, we're going to sprinkle over several of them and talk about them as we go along. So what is the Fermi Paradox? It's kind of a 2-step argument. The first is, if alien exists, they should be here in our galaxy. And if they're here in our galaxy, then we should observe them, right? We have high-powered radio telescopes. We have big optical telescopes. We have been scanning the sky for years. And yet, where is everybody? There is still no solid evidence yet. You start diving on the internet places, you'll find all sorts of crazy evidence. But in the scientific reading, that's right, evidence, just watch YouTube, man. There's full of crazy stuff on YouTube. And what we're going to try to do is shy away from that, right? Leave all of that garbage in the box. Like, what do we know science-wise when we do this? I'm sure we could have a full presentation on crazy alien conspiracy theories, but that's not where we want to go with this. If we look at some of the line of reasoning real quick, There are billions of stars in our Milky Way, like the sun, between 100 and 400 billion stars in the Milky Way. G-class stars, we have a G-class sun, makes up about 10%. So good estimates, 20 billion stars are much like our sun. The high probability that some of these stars have Earth-like planets in the circumstellar habitable zone. We'll talk about that in a split second. There are already 45 confirmed in the habitable zone as of 2026. Could there be as many as 7 billion planets out there? It sounds like Carl Sagan all of a sudden. Billion planets out there. Many of these stars, hence planets, are older than our sun. Our sun is a fairly young star. There are many older stars out there that would have had much longer life periods for life to change and grow on their planets. So if these are typical, maybe these planets developed life years ago, eons before here on the Earth. And then some of these civilizations may have developed interstellar travel to at least to some advanced technology so that they can spread around the galaxy. And yet, we don't know where everybody is yet. Even with a slow pace, if with stellar travel moves really, really slowly, right? We don't have to get on light speed ships or faster than light or any kind of unique physics to get there. It could take hundreds of millions of years, but in 4 billion years for a planet, right, or for a star, 100 million years is yet a drop in the bucket for that time. So several simple simulations that show colonization should be done in our whole galaxy in 1 billion years. And our sun is 4 billion years, which means there's 25% of the lifespan of just our planet, just our sun. There could be civilizations teeming in our galaxy. Our sun's a third or fourth generation star, about 4.6 billion years old, many billions of years older than our sun. And yet, however, there's no yet convincing evidence that our galaxy is full of aliens. So where is everybody again? All right. And a small aside, right? I did this program years ago, but as a small aside, the Drake equation, that is it, right? This is to try to do the math behind just brute forcing how many alien civilizations there should or should not be. This was developed by Frank Drake to try to determine how many civilizations there were to communicate with in the galaxy. Again, this by itself, whole nother photo program that we can do here. But you did this program. I did this program several years ago too. I do it often for the volunteer or the regular Thursday, Fridays that come in here. But again, this is the mathematical side a little bit as to count them. In the Fermi Paradox, it's just why or why not, right? So that's the difference. But I would be remiss if I didn't mention the Drake equation when talking about aliens. A quick map. We talked about planets that were in the habitable zones. A quick map of some of the planets that we know of that are in the habitable zone. I assume that yours are on here somewhere, probably, if they're in the habitable zone, maybe up there. But you can see just already how many planets we found that probably have some sort of liquid water on their surface. The point here is that they're out there, and we're getting better and better technology to understand what kind of habitable environments may be on some of these planets. All right, before we go any further, that was kind of the intro. Disclaimer number 2 is the next series of slides are all hypotheses or scenarios where alien life could exist. Again, there's not any direct evidence to necessarily support any of these. These are all hypotheses to the end of the which helps solve the Fermi Paradox. So in section 1, the aliens exist and they are us. We are the aliens in the galaxy, right? So they're here, or at least we're here. They exist, they're us. We're all aliens, goes the hypothesis, based on the idea of panspermia, which means that the seeds of life are everywhere, and we'll talk more about that in just a second. We have an idea. There are amino acids in space, sugars, and other complex molecules floating around. can these then complex molecules survive? There are more than 130 molecules already found with 4 or more atoms in there. I did a presentation years ago on the molecular clouds that are out there in the galaxy. And by looking at the radio frequencies coming from those clouds, you can decipher some of the atoms or some of the molecules, not atoms, molecules that are out there in space. Here are just a handful of them already as big as nonane, right? That's a 9-carbon chain that have been strung together that they've been able to find the radio signatures for in space. Glycine, a simple molecule for building blocks of proteins. Dimethyl sulfide, a gas that is solely made by living organisms here on Earth. I'm not saying there's not chemistry out there that can create it, but we've seen it out there in space. And then hexamine, found in meteorites, right? A building block for the organic life here on Earth. So as we do the science, as we look out there more and more, we see some of these molecules that could be just floating through space. And on the time scales, they're no longer a problem if these seeds have been everywhere, right? You'll say, oh, there hasn't been enough time yet on Earth. There hasn't been enough time on some of these planets. If all of the molecules of all the seeds are out there in the universe that are constantly landing on these planets, is that where the life comes from? Is that why we're here? So the alien among us theory, the second one, aliens have been here all along, been intermixing with our species. Some people say Neanderthals, right, or whatever, but they've been here. Maybe the aliens are just too advanced. Maybe they're here, but they're too advanced for us to notice, right? You know, when Cortez landed in Mexico, do you think the ants noticed? Right? Is that the kind of gap? If they're 1 billion years ahead of us in technology, are they just unobservable for us? So let's talk more about the panspermia, because all that alien among us stuff is kind of crazy. One, this idea dates back to the Greek times. It is not new just to talk about, is there the life molecules out there or life out there? Work in the 19th century focused on the more modern form, which is lithopanspermia and microlithopanspermia, which is the idea that there are meteorites and micrometeorites out there in space that are constantly landing here on the planet. I forget how many tons of micrometeorites we pick up every year on planet Earth. Did we do a project? I know there are projects where you can go up onto your roof and put out a pan, put some magnets on the bottom of it, and you can actually collect micrometeorites from outer space. They're constantly falling or collecting onto planet Earth. Meteorites or dust grains can deliver the molecules to the planet. Kind of radiopanspermia is another model or another idea that the space is full of spores or molecules that are driven through space by the solar winds or galactic wind, right? Think of them as streams of photons off of our star. And then these spores, these molecules land, and wherever it's feasible for life to continue to grab and take hold, they then move forward. Life then moves forward. And then there's the AI picture of it. And then something called necropanspermia, which is that dead bacteria or viruses are floating around in space. And there's enough organic molecules in those that when they land on a planet that is habitable, life can then start based on those molecules that have been ejected off of their home planet. In other theories, aliens were here in past before human beings. Again, the evidence, they say the Sphinx or the Clovis points, etc. Again, jump on the infinite rabbit hole of the internet and you can find that list. Goes on forever. But the Silurian hypothesis, do we have any Doctor Who fans? What? Really? Okay. The Silurians, right? It's a thought experiment based on modern science's ability to detect evidence of these, of what could be advanced civilizations in the past, perhaps millions of years ago, that landed on the planet. Stop and think about everything you see around us and the weather and tornadoes and hurricanes and everything getting ground down to dust through erosion. What could possibly still be here in 1,000,000 years? Right? What evidence that we would ever hear in 1,000,000 years? I can only think of one thing that I have a good state that says it would still be here in 1,000,000 years. The pyramids will be gone, right? Fossils will most likely be gone or turned over, right? Some fossils maybe, but our radioactive nuclear waste will still be around in millions of years because the decay is so slow and it will look out of place. Right now, maybe it gets smeared out through plate tectonics and things, but that our radioactive nuclear waste would show up as an anomaly on this planet. Is there something, were they ever radioactive, or did they ever have the Silurians, right, whoever they are? So it's just a scientific thought experiment of how would you detect a species on the planet from 1,000,000 years ago, or 5,000,000 years ago, or 10,000,000 years ago. Doctor Who. All right, there's my Scully and Mulder, right? Your X-Files fans that are out there. You know, other theories. The government's hiding the proof, right? Oh my Lord, you can hear all of that on the internet too, right? Are they watching us from UFOs, right? Are they somehow invisible, cloaked, right? That allow them to be out there but not detected from us. Here's the reported UFO sightings. Apparently, you have to live in America or England to see UFOs. They don't go anywhere else. Just those two spots on the planet are where the UFOs are hiding. And it's that kind of evidence that drives me bonkers too. Like, oh, I've seen them. No, nobody else sees UFOs, right? What the heck's going on? Dear Lord. All right. In section 2, we have the aliens exist, but we haven't been able to observe them yet. And they call this the dark forest hypothesis, right? That we live in a big, enormous universe, and we just haven't had the time to find them out in space. It's a big dark forest out there. There's lots of species, right? Even on our own planet, the ocean is very deep. Every once in a while you hear, oh, we found a new species of jellyfish or fish on the ocean floor that we never knew existed before, right? Is that why we don't find them? So we call it the the isolated Earth, and I call this the naturally section, right? So by the laws of physics, they don't forbid interstellar travel by any stretch of the imagination, but boy, they sure don't make it easy, right? I mean, there's a lot of gaps between the stars. Distances, the stars are just too far away. We are naturally isolated in our little section of the galaxy. For example, Voyager travels at a very pokey point, quadruple 5.8 or times the speed of light. It's going to take 73,000 years just to get to the next closest star. Even at 0.01 which is, still astronomically fast, right? 480 years to get to the next closest star. Even at 1/10 of C, Epsilon Eridani, the next closest sunlight star, is still 105 years away. One entire human lifetime, right? Like if you have the baby on the space shuttle, right? On the day you launch, he or she will be 105 at 0.1 speed, right? So it's not easy to move amongst our galaxy's stars, right? And then maybe these distances are just too great for life to overcome, right? 4 light years to the next star is just too much for us, too much for life to be able to handle and overcome. The next one is time. Simulations show the galaxy should be colonized in a few million years. There seems to be plenty of time for that to happen. We can include rates like factors like the rate of travel, settlement establishment time, number of ships per settlement, settlement lifetimes, et cetera, et cetera, et cetera. It would be a cool photo program to put us into groups and run a simulator and see how people think, or the groups think, that life spans through the galaxy. Real quick, another quick aside, spacecraft is saving the solar system. This is from heavensabove.com. There are currently 5 of them, 5 spacecraft, Pioneer 10 and 11, Voyagers 1 and 2, and the New Horizons space probe, all have escape velocities from the sun greater than 1, so they can make it out and away. They're never coming back to Earth. They will never stay in orbit around the sun. They are interstellar messengers from there. And the date to note will be November 13th of this year. Voyager 1 will be 1 light day from Earth after 40 years or whatever it is, right? We launched it in October 1977. The signal from Voyager 1 will take 1 day to get back to us, and if we want to communicate, it will take 1 day to get out there. Just the ideas we talked about, 0.01 C or 0.1 C, and how fast things are going. The fastest human-made object ever is the NASA Parker Solar Probe, 0.0064 C, as it went around the sun in one of its orbital loops several years ago. That's the fastest we have ever gone, right? So maybe these distances are just too much for life, at least as we know it, to be able to get off of this little rock of ours. So galaxy simulations, diffusion, random process where life energy just spills slowly out into the galaxy. Does life movement follow the same pattern? There's a percolation theory that says this is just a flow through, so no special physics. It's just a slow path to each star system. It's not just random, but it's from star system to star system. And it's kind of the path of least resistance that life would take to get there. And the colonies would be weakly connected. And then we have what they call stellar automata, which is the method for modeling the diffusion through the galaxy. Have any of you guys seen the Conway's Game of Life kind of thing? Yeah, this is where you would set up specific rules for every star, and you would watch how the life moves or tries to move about it based on all of those rules that you input into the system. And again, kind of a cool idea to get 4 or 5 people together in a group to try to think of what those rules are and then run a simulation and see what happens. Does everything just die out? And how many times when you put in the pieces of the program does it just never make it? It just dies all the time, all the time. And then if you can just unlock the right set of requirements, then you can see it expand throughout the whole galaxy. But maybe it's not easy, right? Laws of physics don't make it easy for us. Again, maybe a future photo program in 2028 at the rate you're going on that. All right, so that was that was life is isolated naturally. Now we have the isolated on purpose category, for which the aliens are doing something to keep us isolated so they are not being seen, right? So another good example is the zoo hypothesis. Yeah, we just live on our own little cage trapped here on planet Earth, and the aliens are sitting back just checking us out, right? They're just like you walk by the Cincinnati Zoo, the elephant's in the cage, you kind of look at them and go, yeah, that's kind of cool, and walk along, right? Maybe the same thing's going on. They just keep us in our own little cage, and they can observe us whenever they want. The interdiction scenario, this is the no life is being to be interfered with. We also know it as the prime directive. Any Star Trek fans? Yep, all right. It says, unless you have light speed, unless you've gotten to some technological barrier or you've crossed over it, then you're allowed to join all of the rest of the civilizations out there in space. We have not crossed that threshold yet, and therefore we stay isolated, right? We're not to be bothered. right? Keep calm and follow the prime directive. The planetarium hypothesis, this one's kind of crazy. Maybe we just all live in a simulation, right? There's a computer running it. We look out in space. We see those things that are out there. Go back to Copernicus in the old days. And then, we're isolated because alien cultures don't have the drive, right? We think, oh, we got to explore, right? Since Christopher Columbus, we've got to go out, we've got to explore, we've got to go see other areas and, get ourselves off this little land area that we have. But maybe there's no drive to colonize the galaxy. Maybe there are lots of planets out there with life on them, but nobody wants to leave. Everything is just on. We come to accept our fate that in 4 billion years, your star blows up and that's it. Thanks for playing the game, guys. And off you go because it's too expensive or, ethically, they don't want to come and drop onto planet Earth and bring all their germs and wipe out the life that's here. There are time barriers, changes in philosophy, right? The next guy gets elected and says, we're not going to the planets. The next guy gets elected, maybe we will go to the planets, right? Or they're isolationists. No, nothing out there. We're going to stick to ourselves and keep our own planet as the way they are. Or another interesting theory is they're non-consumers, right? We think of ourselves as the intelligent life to go out there, but we need stuff to live, right? We dig it out of the ground. We have to eat. We have to breathe in the air. But maybe they're not consumers. Maybe they're just producers like plants. They don't have to go anywhere. The plants are thrilled to be here. They don't need something else to stay alive. They're getting their energy from their star or from their sun, right? So maybe there's just no reason to go out. Maybe the world is full of producers, or the universe or galaxy full of producers instead of consumers like ourselves. All right. So if we're isolated by ourselves, what about the communication, right? Oh, we're sending radio waves out all the time. We're sending out information. Maybe the aliens are signaling. We just don't know how to listen, right? I mean, we have our radio telescope set up. Who says they're broadcasting in radio waves, right? Wrong frequencies, narrow bands. There are millions of bands to choose from. Are we just not listening to the right ones? Few candidates exist, though. Let's make a little science note here. We have the WOW signal from August of 1977, and then another one in 2002. Nice narrowband sharp signal that showed up. No idea what it's connected to. Don't know why, but it was there. It looked exactly like we would expect a narrowband signal to look like, but we don't know from where it came, and we haven't been able to replicate it. Just random? I don't know. It looks exactly like we wanted to see it, but there are examples of narrowband frequencies. There's the picture of the WOW signal. I know you went to Big Ear. You went to Big Ear. A couple people went to Big Ear several years ago before they tore it down. They had this on the wall. Jeremy Ellerman, I think his name was. He had circled it and written WOW next to it because in a world of ones and twos, he gets a Q and a U for crying out loud, right? That's how intense that signal was coming through the Big Ear radio telescope. And then that's just radio frequencies, right? When we talk about narrow bands, but could be radio or microwave or lights and lasers, X-rays. Doesn't have to be radio frequencies, right? It could be any number of the wavelengths to communicate through. Maybe the signals we talked about those distances. Maybe the signals are just too far away and they're too weak. We don't have big enough telescopes yet to listen through all the noise that's out there, or they're just too faint for us to hear, right? Or, there's our signal from the biggest telescope that we sent out in the 70s out to M13. That's the signal we sent out to say, hey, we're here on Earth. It'll get there in about 26,000 years. Someone there will decode it and send back a message 26,000 years after that. And so in 52,000 years, we will dissect the messages from M13 based on what we sent them. There's a half a FOTO program right here too, by the way. You can pick through that also. Doesn't even have to be wavelengths, right? It could be particle signals. Maybe they've controlled and harnessed to communicate with neutrinos, right? In as simple as Morse code, right? You just send out beep, 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 and then it's a string of 5 of them, and then beep, 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 a string of 5 of them, and it can communicate that way. But no one's looking. No one's, I guess we don't have detectors that could pick them up coming in like that. When they do, how about gravity waves? Maybe they're out there and they're communicating by creating gravity waves that they know will travel throughout the universe, right? To look. We just invented and just found our first gravity wave based on 2 black holes that smashed together somewhere in the galaxy, several million years ago. But maybe that's the way they're communicating, right? Or faster than light, tachyon signals, right? You have the stuff from Star Trek. Can we communicate if they exist faster than light, right? There's a whole branch of science looking for this kind of crazy stuff. But maybe we can't communicate because we just don't have the technology to listen yet. Communication, they're signaling. They're saying, hey, we're here, but we don't know where to look. It's an awfully big sky out there. There's a signal. We're just missing it because it looked like noise to us, right? Here's the gibberish that comes out, the noise, and then right in the middle is that signal. Maybe you can see it if you look close enough, but that's what, there's a lot of radio frequency traffic going by. There's not enough time. We've only been listening for 100 years or so, ever since, oh my goodness, I'm getting old. Yes, Marconi, transmitted over the edge of the horizon, right? His first thing, he transmitted from land to a ship beyond the horizon. That was the first moment that we didn't have to look at each other to communicate. We could be across the, around the world or across the ocean, right? And that's been less than, just over 100 years ago now. Everyone's listening, no one's transmitting, right? Everyone's out there. What do I hear? What do I hear, right? But no one is transmitting. There's one group of us that's transmitting, and that's planet Earth. But maybe no one else is transmitting. Maybe everyone's just listening. You ever think that we're the noisiest FM radio source on this side of the galaxy, right? Constantly dumping FM radio out into the space. Anyone see Contact, right? The Ellie, her first thing back is the 1932 Olympics. I think it was 32 or 36 Olympics. And that was the first thing we broadcast out into space, right? We just continue to leak FM radio out into space all the time, right? Or there's no desire. Those guys don't care to communicate. Maybe they're producers and they don't have the technology, or they just don't have any reason to want to communicate out into space. Last one in the communication is the message in the bottle theory, right? Maybe they're communicating, it's just not at light speed. Oh, there's Voyager. There we put it out there, 73,000 years to the closest star. Takes a long time, right? But okay, how it goes. If they're leaking very slow communication through probes or whatever, they just haven't had time to get here yet. Other reasons, L is very short, right? This goes back to your Drake equation. Civilization lifetimes don't last very long, so there's no way to communicate because they don't last long enough to stick around, right? And this is the natural section. So we have biological, biotech, nuclear war, AI tech, climate change, anything else we can do to ourselves possibly, right? And wipe ourselves off the planet. Maybe the universe is just way stranger than we can imagine right now, right? We learn new stuff all the time. And as it's just, if you were 1 billion years more advanced than here on planet Earth, what else would we know, right? What else would we learn about it? Intelligence isn't permanent. Who saw Idiocracy, right? Yep, a couple people. Evolution's not hierarchical. We don't keep stepping up, right? We adapt to our changing environment. Maybe we get dumber over time and we're unable to communicate. Look at you laugh, right? Like, all right? In this room, there are probably a couple people who can build a radio, though, right? And say, yeah, but, you sit in high school, yeah, I think really smart. You want to build your own radio? Can you build a cell phone? Can you go into your garage and communicate? No. Like it doesn't take very much to reverse and not have that permanent intelligence. Again, evolution's not hierarchical. I know that's your heresy on occasion, but yes, right. You see, Wally's another good example. Absolutely, absolutely. Or the galactic super predator, right? He goes around, he or she. Look at the long hair there. Goes around and devours civilizations that get too noisy in FM, right? They show up, they're consumers, they sweep everybody off the planet and eat them up, and off they go, right? Looking for the next radio source that's out there. That's why we don't hear from anybody, because they're all dead, right? Like, oh, that'll never happen. That's the dodos, how well it went, right? There are lots of extinct animals on this planet because the predator, the super predator on the planet, went and killed them all. And you're like, oh, we all laugh. But then you think about it, you're like, that's not as funny as I thought it was a minute ago. All right. So next section, we did the one that says there are aliens. We've done the ones that says they're maybe we're isolated. Here's the depressing one. They really don't exist, right? This is kind of the rare Earth hypothesis. Quick disclaimer too, some of this data is a bit old. You saw a little bit of that early on when I showed you the pictures of the of all the habitable planets, or the habitable planets in the habitable zone. I'm on that. In the next few slides, though, can be found in Peter Ward's book, Rare Earth, copyright 2000. So a couple, like I said, a little bit old. That's what it looks like. We'll go through real quick. What makes life rare? The galaxy is a dangerous place. Why is Earth special? And then finally, we'll go through a quick synopsis of the Great Filter. What makes life rare? Life has only emerged recently on planet Earth, and what I mean by that is intelligent life. Right, for the 4 billion years that the Earth has been around. If we argue that human beings have been here for 2 million years, plus or minus, but if you write the definition as intelligent as the only time when you can communicate off planet, that makes us only a couple hundred years old, right? So maybe life has only emerged recently, the last couple hundred years. Planetary systems are rare. That's that old data thing coming out to get me. Rocky planets are maybe yet rarer still. We can have a lot of planets. The first one, planet around Pegasus 51, was a supergiant gas giant like Jupiter. Maybe that rocky planets like Earth are yet rare still. Even if we're rocky, doesn't mean we have water, right? So that's even yet rarer. There's water world. And then maybe the habitable zones around these stars are just too narrow. That's, again, an older thought process. The more we learn, the more we think we find those planets in there. The galaxy or Earth is a dangerous place. Supernova explode, wipe out all life within a certain radius around each star. Every time they go off, that's huge amounts of radiation that goes out and breaks up organic molecules across the galaxy. Right? Betelgeuse, or the armpit of Orion, if and when it supernovas, I hope it's at daytime for me, so that the Earth is between me and all of that radiation coming off of the wavefront of the blast when it goes supernova. Gamma ray bursters, again, high energy, sterilizing the space around it. Super volcanoes here on Earth. Eruptions like Yellowstone several tens of thousands of years ago wiped out most of the life in North America. Mass extinctions that occur. Asteroids, you can ask the dinosaurs how well it went for them 65 million years ago. Changing our star, the sun changes for whatever mechanism. It doesn't have to change very much to make life very annoying for us, right? I mean, if the sun were to brighten by 4% or 5%, that's enough to cause enough heat on the planet that it's not viable. If the sun dims a little bit and were to somehow lose its intensity, it's going to get really cold here on Earth. Earth has already been through a great snowball. For about 50 million years, most of the Earth was covered in ice 700 million years ago, right? And so If that happens again, we would be done for. That's well-established science. You're looking at me like I have a rock in my head. I didn't learn about that either until recently. And there's a picture, obviously AI generated, for what they thought the great snowball may look like. What makes Earth special, right? So if it's rare, what is it that makes it rare? Maybe we're just the optimal pump for evolution, right? We have plate tectonics. We have axial tilt. We have the orbital and seasonal timings, right? We have what maybe 1 year or about 300 days is just about right to get the evolution pump running to get it going, right? On Mars, it also has seasons, but they're all twice as long. Maybe that's not the right cadence or rate for us to get the evolution pump moving, right? Maybe Earth is just the first to life. Not that, but maybe we are. The moon is unique, right? When we look out in space, we don't see a lot of double planet systems. Maybe Pluto, you might be able to buy that, but Jupiter is much bigger than its moons. Smaller planets like Mercury and Venus don't even have a moon. So we had a catastrophic impact. Mars-sized body hits the Earth, rips a third of it off, coalesces. We get our moon that orbits around the Earth, tidally locked once every 28 and a half days, 29 and a half days from cycle to cycle, depends on how I want to count it. That we get, that makes us special, right? That helps stabilize our axial tilt. That gives us, something special for life to hold on and stay on Earth. So it's a dangerous place. Sorry, I'm pushing the wrong button. All right. The next thing we want to talk about is the great filter. And this is the last section of the program here. According to the great filter hypothesis, at least one of these steps in the list to be complete, but must be improbable, right? So as we move through the steps that science thinks, maybe there are other steps, one of them has to be improbable, right? So we have to have the right star system. We have to have reproductive molecules in some way so that life can continue to advance, right? Do we need some sort of simple cellular life, complex cellular life, some sort of sexual reproduction to be able to drive forward the change and the evolution? If we just kept making the same cell over and over and over and over and over again, it wouldn't really evolve as quickly as we do when we mix the DNA, right? From there, we get tools or intelligence, and then a civilization advancing toward potential colonization, and finally, the colonization of the galaxy. This, again, could be a whole photo program unto itself for the great filter. I just want to touch on it quickly. Right? Oh, the great filter. All right. So here are all these filters, right? The origin of life, and then we go along, and there's a filter, and then species pop up, or life pops up. Can it make it through that filter? Can it make it through from prokaryotic life to eukaryotic life, right? It has to cross through each one of those filters. Are we on the left side of this chart, the one that is the great filter, the one that is the hardest to overcome, right? Where all of the life is teeming over here by itself? Or are we the one who has squeaked through and we're by ourselves on the right side of the filter, right? Headed toward the type 3 civilization. So there's just the common evolutionary leaps. Do we make it past? And so here we have the example that the great filter is behind us. Maybe eukaryotic life is the great filter, right? And we've all overcome that, right? Every one of us has a cell nuclei in the middle. Maybe that's very, very difficult for nature to handle. And we have crossed it. And that's why we're all by ourselves. We're the only species in the whole entire galaxy that has pushed its way through the great filter. And we're by ourselves on the other side, right? Here's the evolutionary leaps we haven't even thought of yet, right? We're not even approaching other filters that are still yet coming before we can be a type 3 or a civilization that expands itself to the stars. All right. The next one is we're on the left side of the great filter. Maybe there's a step coming up that we don't know about yet and that we just never get to. We'll never be an intelligent civilization. We will never get to become a type 3 civilization because we're not going to make the leap. The great filter's in front of us and we're going to hit it like a brick wall. Wham, right? That's it. Thanks for playing the game, guys. You didn't make it. If this is the case, we could be in trouble, right? That's where we get stuck. And so, is this the end of the topic yet, or only the beginning as we move through? Like I said, there could be several photo programs built into this. And of course, you know, going in, right, we knew that there wasn't going to be some aha moment that Craig whips out the evidence the aliens are here, right? I'd be a lot richer if that was the case, for darn sure. But it was only the beginning of additional hypotheses that we could think of for why the aliens, we don't see them or observe them here on planet Earth. That is what I've got. Any questions, comments, concerns? I know I left you with like a ton of stuff there. Here we go. Yeah. Yep, go ahead. Mm-hmm. My guess is yes. If you had a Arecibo style telescope pointed at the Earth, you'd probably, it's only 105 light. No, how far? 10 light years away. So I think you could pick up the radio frequencies. I don't know. We got to know someone else who does better math than I do on that. I think that's my thought on that.
Anything you send out here, like,
Yep.
By the time it gets to Pluto, it's so far down in the noise.
Okay. How about like military radar? Like when they send out pulses that know? Okay. All right. Narrow band frequency then. So. Yep. Okay. Gotcha. So no on regular just leaking information. You'd have to send it perfectly to Epsilon Iridon. Mm-hmm. Yes, and it's only one day. Yeah.
Noise is the issue.
Right.
And the universe is big
Noisy place. Yeah. Gotcha. Yep.
Here's my solution.
Oh. Okay, go ahead. You have a solution.
Probably blasting energy.
Mm-hmm.
And we can't build transmitters powerful enough. Yet we're orbiting one.
Oh.
We need just a big shield. All we need to do is open it.
Oh. There you go.
At the starlight, somebody will take notice of that.
Sure. Well, in a sense, we notice when we have eclipsing binaries, right? Like if you could control it so it was not steady, right? That would certainly set off an alarm. Whoa, wait a minute. The pattern is a list of the prime numbers, right? Then somebody would say, wait a minute, right? That's kind of bonkers if that's coming off a star, right? Dyson sphere style, right? Where you're able to open the gate, you know? Well, picky. For us, right? If you're a billion years more advanced, maybe we just make it spin real fast. I don't know. On that Dyson ring, there we go. That's big enough to block the star and allows the signal to go out when we do that. That's kind of a fascinating idea. Yeah. Sure. Yep. Question.
Two things. One is that experiment is actually
Oh.
people.
Oh, okay.
Turn them over. So small.
Sure. Okay.
My question was going to be about.
Mm-hmm.
put in your own estimates.
Sure. So what I should do, and I haven't done this yet, I should run it as like a Monte Carlo simulation, where I take all of my ranges, because the several times I've done it, I either get like, yep, there's certainly life, right? It's all over the place, or yeah, not in our galaxy, right? Because I pick the low ends and I pick the high ends, and then, I get the extremes. I don't know that I have an exact answer, but what I should do is like run it, just put it into Excel and run it 10,000 times or 100,000 times with the ranges that we get better and better at. Science is really cool that we keep pushing ourselves down that equation, right? I mean, when I was a kid, there were no extrasolar planets, right? And now, we've seen dozens and dozens of them, right? It wasn't long before, I was born that, Stanley Miller did his experiment where he was able to generate organic molecules in a vessel from nothing, with just lightning, or with a spark generator and a boiler apparatus, right? So we keep pushing ourselves further and further down the Drake equation to help narrow in what we think those values could be. That's right. That is going to be the big driver, right? Exactly. Like, maybe, what was it? N equals L was the actual real answer, that the number of civilizations is equal to the length of the survival, because it always gets there and then they die off because L is not able to sustain it for any great length of time. So far, yes, right, yeah, a bare sliver of time.
Just say that if anyone's interested in what we're talking about, the Frank
Drake.
equation,
Yeah. We can.
equation is online, and you can actually put in your own numbers online. It's fairly outdated. They've refined it a lot.
Oh yeah.
They refined it a lot, but a lot of these websites make it very simple. It looks kind of complicated out there, but it's just multiplying probabilities.
Yeah.
It's fairly easy. So they'll take you to the website and take you through it. Just look for Frank.
Drake. Come on, I'll get there. Hurry up, hurry up, hurry up. It's like section 1 of my, there it is. Right, yeah.
It's complicated, but it's really just multiple. And these websites, we just walk through it. But it's kind of fun to do, just to see what you think. And that L is a big thing. Because when I was teaching, we teach college students, I teach high school students, and they do it here too, and you get all sorts of numbers for that.
Yeah.
How long things are.
And most of the numbers are either somewhere between like 0.1 and
Sure, okay.
you multiply them all together and it works out to 1,001. We see L equal to N. Red equal to L.
That's right, yeah.
We've been doing PMA for 100 years. That says there's a better civilization.
Oh yeah, it's,
That's not very much.
and L is driven by both those natural factors as well as what we do with ourselves, right? Like asteroid, dinosaurs, and I'd argue we've done it at least several times on planet Earth, right? Where we get a mass extinction. The dinosaurs were around, for hundreds of millions of years, right? The pyramids are closer to the T-Rex than I think the Stegosaurus is closer to T-Rex, right? That just gives you an idea about how much time dinosaurs were on the planet, right? And were they really smart? I mean, I don't know what fossils that said they were really smart, but the asteroid came along, time to start over, guys, and wipe them out. Is there something in store for us like that before we do ourselves in? Don't know, right? I mean, that's, the Hantra virus is going to take us all out tomorrow, right? Who knows what's going on? There's a cruise ship, guys, if you're not up on current events. Yeah, that's well, yeah, pandemic, whatever the case might be. I don't want to ever say that word again. I saw flashbacks from a few years ago. Holy moly. Yeah, sure. Anyway, all right. Well, thank you guys. Thank you very much. I appreciate it.